Hi, we're group 32. We're going to do problem 4.65, which is to draw the shear and moment diagrams for a frame. Alrighty, this is our overall frame all put together. You can see there's a distributed load from C to D, and then there's 2 point loads on the top beam, BC. It's worth noting that A, C, and D are all pin connections so that they support no moment, while B is a fixed connection which will support moment.
This is our free body diagram, which we have split into 2 parts, A, B, C, and C, D. We split the frame at pin C because it does not carry moment like it would at point B. As you can see, we've shown the reaction forces at pin C going in opposite directions, as well as the distributed load as a resultant force, so that we can easily find the reaction forces.
Alright guys, here comes some statics. You'll notice that we've split this thing into 2 columns where we've been working on it. We've been working on element CD on the left and element ABC on the right. Step 1 here is to take the sum of the moments about D, which is the ground connection on the right side of the frame. What we did was just add everything up, take the moments, and you will find that C horizontal is equal to 45 kilonewtons to the right. Second step, if you take the sum of the horizontal forces again for element CD, you'll find that the only thing you don't know then is the horizontal D force, which comes out to be 45 kilonewtons to the right as well. Next step, we come over here, we're going to start working on element ABC now. If you take the sum of the moments about A, which is the ground connection on the left side of the frame, you'll find that the only unknown that you have in that is the horizontal C, or the vertical C force. You add all that up, do the multiplication, a little bit of math magic, and you'll find that the vertical C force is 7 kilonewtons upward. Next step, still looking at element ABC, let's take the sum of the vertical forces. Then you have AV plus CV minus 90 equals 0. Your vertical A force is thus 83 kilonewtons upward. Fifth step, we're going to start looking at element CD again now. The sum of the vertical forces is equal to 0. dV minus CV equals 0. Therefore, dV is 7 kilonewtons upward. Last step, sum of the horizontal forces, this time for element ABC. A in the horizontal minus C in the horizontal is equal to 0. Therefore, A horizontal is 45 kilonewtons to the right. One thing about these beams that often confuses people is that the same force can be an axial force in one beam and a shear force in another beam. Take for example this force. This is the same force in both of these pictures, and these two come to a joint right here. However, the axial force in the first member becomes a shear force in the other member because it's acting in the same direction. So it's an axial force down the axis of symmetry of this, but it's a shear force for this. Likewise for these two. An axial force in the horizontal member here becomes a shear force in the vertical member.
Here we have the shear and moment diagram of element AB, and starting at point A, we see that there's a force to the right of 45 kilonewtons. So starting at 0, we move down 45 kilonewtons, and then because there's no changes along the element, we just keep a constant line all the way up to point P, where there's another reaction force going 45 kilonewtons to the left. So then for the moment diagram, starting at 0, we see that we use the area of the shear diagram to calculate this point, shown as negative 45 times the 4 meters along the beam. So then, because there's a moment at B known to be 180 kilonewton meters, it shows that the moment goes back to 0.
So let's start looking at the shear and moment diagrams now that we've found all the reactions. We know that there is an upward reaction of 83 kilonewtons and 7 kilonewtons at C in the vertical, and then there's 2 downward loads of 50 and 40 kilonewtons respectively. So let's start looking at the shear curve. The very first reaction in this is an 83 kilonewton upward reaction. That's going to push our shear from 0 up to positive 83 at point B. Now, since there's no loading in between B and the 50 kilonewton load, it's going to stay constant at 83 kilonewtons until we reach this downward 50 kilonewton load. At that point, it's the shear force will go from 83 down to 33 kilonewtons, because that's the original 83 minus the 50 kilonewtons that the shear just decreased at this point. So, let's continue along the beam. The next force we encounter is the 40 kilonewton load. That takes our shear from 33 down to minus 7 in the same fashion that it went from 83 to 33. Continue on more, we get to the 7 kilonewton reaction, and that'll push us back up to 0. Since the shear is 0 at both sides, then the beam is in equilibrium. Let's look at the moment now. B is a fixed joint, therefore there will be a moment at point B. It's computed to be negative 180 Newton meters. Now, the most complex part about these is figuring out where your moment curve is going to fall at each force. So, let's start looking at the 50 kilonewton force. If you take minus 180 plus the area under the shear curve from 0 out to this point, it'll tell us where this is going to fall. So minus 180 plus 1.5 meters times 83 kilonewtons will tell us that this point is going to be minus 55.5 kilonewton meters. Likewise, you can find that this will be 10.5 kilonewton meters by using the area under this plus minus 55. And then likewise, you can move along to 7, and it will end at 0 since there is a pin joint at C which will support no moment. Alrighty, let's look at this last member. This is CD, and this is a distributed load of 15 kilonewtons per meter, so this one's shear and moment diagram is going to look a little different than the rest. Namely, this distributed load is going to cause a linear shear diagram going from negative 45, which is the reaction here, to positive 45, which is the reaction at D. So, taking that in mind, we can then see that the moment curve is going to be quadratic since the shear curve was linear, and you can find the relative maximum of the moment curve by taking the area under the shear curve from the beginning to where the shear curve goes to 0. So, the shear curve is 0 at 3 meters from point C, so we can find this value of 67.5 by saying 45 kilonewtons times 3 meters times a half to find the area under that triangle. The value comes out to be negative 67.5 kilonewton meters, so that's the maximum of the moment curve, which also falls at 3 meters from point C. It's going to be a quadratic curve, and you know it's going to start at end at 0, since those are pin joints, so it'll go from 0 to 67.5 back to 0.